Hello, this is Abhilash Majumdar, and today we are going to talk about SYCL, Integrated Compiler Runtime for Accelerated Deep Learning. This presentation is mostly about what the SYCL language is, how it can be used to build applications which can run on different hardware vendors and different platforms, and how we can leverage the cross-platform runtime abilities to design more sophisticated deep learning applications, as well as understand a little bit about the DPCT compiler backend, which processes the SYCL language in general. So let's get started. So before we start, just a brief idea about the fact that in today's world, there are a lot of generative AI and LLMs being in place. And majority of the LLMs are nowadays working on accelerated hardware abstractions, such as CUDA or HIP. And SYCL, being one of the accelerator interfaces or languages, is also often used to optimize and build scalable and faster products in case of deep learning. So with the help, the only advantage of SYCL is that it can be used to run on different hardware vendors using the same code. And in the today's world of exascale computing and different deep learning platforms, like let's say TensorFlow, PyTorch, device-specific runtime and device-specific codes are very much needed. That is where the interface, or I would say the amalgamation of different kind of runtime accelerator interfaces come into the picture. The only advantage here is that with the help of SYCL, you can run the same code across different hardware accelerators, and depending upon specific ISAs that your hardware might support, you can also leverage different kind of compute capabilities. So we are going to cover briefly about these different contents. Firstly, the scope of the presentation, what we're going to cover today. Then it will be followed by some LLVM nitpicks and how it interacts with the DPCT compiler to process and compile and build the SYCL code for different hardware vendors. We'll be talking about this introduction to SYCL, and we'll be learning about the SYCL semantics and the language. We'll be writing some custom kernels with some PyTorch case study. And we'll be focusing mainly on auto migration and how to see the DPCT compiler can help to migrate CUDA code to SYCL. And we'll be ending with some performance results and some question answers and references. The codes are available at this particular repository, and it's in this open sourced. So a brief idea about the scope is that what is and why do we need SYCL? So the idea is code once and build anywhere. So SYCL is one cross-platform language that can help you to write sophisticated kernels, accelerated codes, as well as different kind of numerical and high-performance computing kernels, which you can build for separate vendors, separate ISAs. It includes not only GPUs but also CPU FPGAs. As well as you can segregate the code depending upon your host runtimes as well as device runtimes. The major advantage of having this is to write the code only once and use the static code that you have written to deploy in different kind of hardware vendors. So the key takeaway is that build once and deploy anywhere. Where does the cross-platform SYCL language come into the picture? In the case of most deep learning, not only in deep learning, in most scientific computations as well as HPC as well, SYCL is almost comparable to the NVIDIA standards or the CUDA acceleration samples. And today we are going to understand a little bit about how the SYCL language can be used to, amalgamate and use high-performance computing as a way to leverage and build different kind of kernels which can optimize the compute. We'll be understanding a little bit about the semantics of device and host parallelism, since SYCL is one of the languages which is infused with the heterogeneous parallel computing model. So we're going to understand about how the different aspects of the C++ features, standard C++ features of 17, which are included hardbind inside the SYCL language, as well as how to infuse and create and write optimized kernels. The effects of deep learning is something that is one of the prime areas of today's discussion. And we'll be also looking into compiler, DPC++ compiler for auto migration of CUDA to SYCL code, and the different ways how we can do that. So a little bit about the LLVM compiler backend. In the case of Intel, we have an extension over the standard LLVM compiler, which is the Intel's LLVM compiler, which holds in place the DPC++ toolkit, which we'll be studying a little bit later. So in general, the architecture looks like this, where we have the SYCL code or the C++ code, and we boil it down to the CLang or the LLVM extensions, and we use the native C++ runtime to boil down our SYCL code to our standard bytecode, or where we can link with the standard LLVM assembly. There are different compilers inside DPCT, which can help with the drivers as well. So we have the ICX, ICPX, and for the DPCPP compiler. So the ICX and the ICPX are mostly used for the Windows and the Linux subsystem, respectively, and they can help to link as well as compile and build the SYCL code that we are going to write. The ICPX SYCL compiler is the heart of the One API, and with the help of this ICPX command, we can also build for other target vendors, not only SPIR64, which is the Intel standards or the Intel hardware, but also PTX architecture, which is for NVIDIA, as well as AMD GCNs for AMD. This is an idea about what the flow of the compiler backend happens. So we write the front end code, which gets converted to bytecode, and we perform different kind of optimizations in the compiler depending upon the level 03, 02, and we convert it to the LLC format, which is a lower level format, or the bitcode format, which can be transferred to different ISAs for different compute performances. Now we can have different kind of LLVM stack that we use to process and also generate the different kind of results down the line. This is the Intel standards for the LLVM compiler. So ultimately, we have the source files, which are the SYCL kernel files, which gets, and the ultimate result is the fat binary file at the down. As like I said, in the SYCL kernels, we have host and device, two different aspects. So the device part of the SYCL kernels gets transferred, or I would get it's transcompiled or compiled through the LLVM IR and linked to the SPIRV kernels for the Intel side. And now this part gets changed for the NVIDIA side. We have PTX for the NVIDIA, where we have LLVM PTX bindings to convert the particular SYCL device code for NVIDIA systems. And the rest of the part remains the same, where we have the offload wrapper, where we wrap the LLVM specific compiler instruction sets or the instructions, and we get the fat binary file as the final output after linking. So some commands before we go through, because we're going to use these commands down the line. So the most standard command is ICPX -fsycl. This is by default it instructs the ICPX or the DPCP plus compiler to use the fsycl standards, which is the C++17 standards by default. We are going to pass in the source file. It can be any SYCL source file. It can have host and device codes together or maybe separately as well. And we generate the output as we normally would in a separate .o file. For SPV builds, that is the SPIR64 generation builds, which is the Intel standards, we can use that .spv extension as the output, and we can use the LLVM toolchain to again disintegrate and process it further. For the PTX code generation, we can also define what if the kernel specific SYCL kernels are specific dedicated to the NVPTX runtime, then we can write NVPTX 64 NVIDIA CUDA, where we target the XSYCL target backend. So this instructs the SYCL kernel to be compiled for the CUDA devices, assuming the CUDA devices has a minimum of SM50, that is a streaming multiprocessors 50, so that it can compile it successfully and give the results. These are general LLVM syntaxes, which helps to visualize the bytecode in general. We can also use the CLang++ or the Clang++ compiler, but we have to specify the standard C++17, which is the default standard for SYCL 2020 specifications. We should not use any bytecode. If you want to specify the device specific codes only, we can use the fsycl device only flags. We can also use the fnosycl use bitcode so that we get the bitcode format of that. So we can also read from the LLVM assembler after we have the final SPV files in this manner. So This is a human readable manner, so that you can get the CPP files to get to directly get the .ll format, which can be through which you can use the or which you can read the assembly code. So part of this in the repo which I have mentioned, part of the SYCL samples or this particular block reduce, the LLVM codes or the assembly codes are already there in the repositories for reference. So some other nitty-gritty features. So AOT is one of the important features of ICPX compiler, which helps you to delineate what is the runtime going to be. So here we have the marked AVX2 instruction sets. That means the IC is going to be AVX2. So we are instructing the ICPX compiler to have to generate the targets for SPIR64 with AVX2 ICs. So this is extremely important and can be useful to speed up your runs or your compile times when you have dedicated SYCL device codes which are only going to run on certain specific hardwares. So let's say FPGA codes or GPU only codes. So this AOT eliminates different kind of overheads when it comes to GIT. So the no bugs and nothing else. So it becomes extremely fast and you can have the pre-compiled code ready and set whenever you want to run it. There is also one caveat where you can link kernels which SYCL codes which contains the kernels as well as SYCL codes which do not contain the kernels, respectively known as the device and the host side of SYCL. And this is the generic way to do that. So main.cpp does not contain any SYCL kernels. You have the blockreduce.cpp which contains the SYCL kernel codes, and you can link them directly. You can link the source files to them directly, output files for a specific target. AOT has that capability. So now let's move to the interesting topic where we are going to talk about the SYCL semantics. The most important part is understanding what SYCL is. So SYCL is a language, first of all. So it is an accelerator interface language where you can not only use for CPUs, GPUs, but also FPGAs and different other hardware vendors. So the main important part of SYCL is that it has two different aspects. One is the host and one is the device. That means parts of the code is going to run on the host and part of it is going to run on the device. There are three different concepts and three uniquely, severely important concepts over here, known as command queues, memory or the pointers and buffers, and asynchronous parallelism, heterogeneous parallelism. So there are three paradigms. One is the command queues, which is the task scheduler or the orchestrator. We have the pointers and the buffers. Let's think of it like a memory. And then you have the parallel for, which is the, I would say, the synchronous task, the core concept of heterogeneity in the case of parallelism. So SYCL, like I said, it contributes to different kind of ecosystem. We have the Intel's ecosystem where we have the DPC++ compiler, and all hardware supports, different framework support over there. We have the code play extensions of Compute CPP. We have the HIP SYCL, which is now known as Adaptive CPP extension, which is known for the HIP standards as well for AMD GPUs. So some important concepts before we move into the core part of SYCL and the codes as well. So we have something called as unified shared memory, which enables us to work with pointers and let's say malloc kind of syntax in SYCL. Unified shared memory is sometimes quite useful to persist some of the containers or the C++ data structures in the more, or let's say SYCL data structures in a more prevalent manner in the memory. And it has a longer life cycle compared to the other counterparts which we'll be looking into. So USMs are typically one of the robust features of memory in SYCL. There are something called as parallel reductions, which will be coming up. So parallel reductions is something known as parallel for, and these are the main parts of the heterogeneous compute or the asynchronous compute. So it helps us to schedule different kind of tasks asynchronously over a kernel range. So we have another concept called as work groups and subgroups. Work groups are called as, I would say, 1, 2, or 3 dimensional groups of memory, which has different kinds of threads, associations of threads. Each association of thread is known as a subgroup, and they all work asynchronously on different kind of thread items or work items for different kind of processes, for different kind of, computations. We also have CTAD, or the class template argument deduction, which is a standard C++ feature, which helps to classify template instantiation when we are scheduling kernels or writing kernels. We have something called as accessors, which is another important counterpart of the unified shared memory. So accessors are a little bit are very dynamic. They can be have built-in reduction operations and different kind of SYCL operations which are highly optimized. The only drawback being it is quite volatile in memory, and it has a shorter life cycle. We have also, interoperability with efficient acceleration backends, and we also have support for something called a synchronization and barriers, known as atomics. So we'll be looking at each of these parts separately in detail with code samples down the line. So firstly is the memory management. So there are two views of memory, prominently two views of memory. So one is the USM, which is the pointer-based programming, and we have scopes of sharing, automatic manual movement, which is something like this. So we have something called a SYCL malloc shared, which is having the which stores the data structures, or I would say the array in this case, SYCL array in this case, in the unified shared memory, which can be accessed by the device as well. Now, one of the important features is that when allocating or deallocating from the host to the device, it is important to mention that you are either allocating or you are either deallocating it. For example, you are allocating over here, I would say a shared array, right, of size n, right? And you have to deallocate that further. After this wait command, after your processing and your asynchronous tasks queue has completed, this shared array still lives in the memory. So you have to, again, deallocate it back from the device after its computation back to the host. In the case of buffers, buffer accessor is a kind of a different model. So it is a very flexible abstraction over dense arrays of data. And it is used for some intrinsic computations. So let's say intrinsic reductions, intrinsic movements, intrinsic broadcasting. And it has several of the capable features which helps you to get different kind of data structures in C++ standards, which is known as multi-PTRs. So let's say multi-PTR or global PTR, global pointers. So the only there are many features of accessors which helps us to coordinate the address space in global memory, in shared local memory, but the only caveat is that it has a drawback in the sense that it is very volatile. So as soon as you extinguish or go out of the I would say the parallel asynchronous task, it extinguishes. It is no longer present. So there are many advantages of buffers over accessors, buffers and accessors over USM, and we're going to see some of the use cases down the line of this. Buffers are very powerful and elegant, and very much useful in their applications. If there are only specific device codes which you are running, buffers are actually very much useful over USM. USM is a standard pointer kind of notation where you are going to use the DPC++, malloc shared, and different kind of core C++ pointer principles. Use shared allocations when porting code to get functional quickly. USMs are not used for providing peak performance. That is why I said that buffers are more elegant when you have to perform group operations. We'll be seeing that later, where this accessors are actually pretty much useful. So let's look into USM a little bit. So the class of USM looks something like this. So you have a memory which is known as host, device, shared, and unknown. So either of these three enums, these four enums, are going to be present in either the USM device allocation scope aspect, and majority of the times we specify initialize it from the host side, and we pass it to the device for any kind of SYCL kernel computation and back to the host. For shared, if it is in the shared memory, it stays for even longer time. You do not have to copy it back to and fro from memory and so on, from the host to the device memory and so on. So in the next case, we are going to learn about a little bit of the principles of the queue or the task orchestrator or the command queues for USMs. So here work is submitted through queues. So queues are something called as a kind of I would say a task orchestrator, which calls a kernel, calls in all of the data parameters, containers, passes it to the kernel, processes the kernel or the compute, and then sends, I would say, sends all the details back to the memory again. from the host to the device, or it stays within the device. It depends upon the application. So queues are like the central orchestrator. The by default syntax for writing a queue is like this. So you have a queue, which is a SYCL queue scope, and we schedule something with a handler, which is a SYCL handler. So this handler is responsible for writing the SYCL, for orchestrating the parallel for, which is the third important component, or the heterogeneous component, heterogeneous compute component, where we are orchestrating through the queue. So inside the queue, we can have accessors, buffered accessors, or we can have USMs as well. So here we see two different kind of queues, out of order queues, which are, this is actually a linked queue, which is a directly linked to the former queue. So we can have a direct acyclic graph or DAG of the queues one after the other as well. So we'll be seeing some examples on this. So a queue maps to one and only one device until specified. If there is a device selector flag in a queue, which helps to map to separate devices as well. Queues are out of order by default. Work may not execute in the order in which was submitted. So work can be ordered through events or accessors. That is where accessors have another important benefit. You can sometimes schedule your queues to be in order so that your accessors can be so there is no kind of race condition when reading or writing from an accessor, because an accessor is simply a kind of a data structure which is in the shared memory from the buffers. So if multiple concurrent read writes are there, there may be chances of some race conditions happening. So in order to prevent that, we can have in-order queues, which can be useful for scheduling or writing to accessors which are also contributing to some read operations. In-order queues just do one thing after the other. It is essentially easier to reason about than the out-of-order queues. So like I said, this is just a linked DAG of out-of-order queues. This is all of them dependent on one another. And until you specify queue DPCT get in-order queue, which we'll be seeing in the examples, the queue will be by default out of order. So this is how a queue looks like. So my queue is a queue instance, and we submit, and we pass an accessor over here. So we'll be seeing this example shortly. So this accessor has only write, so it cannot read. So there is no kind of race conditions involved over here, because it is only write operation. So, and this is the parallel kernel, which is the heterogeneous compute part, where we are using this handler, right, to create a lambda, and then we are writing to this particular accessor as we normally would as in an array in C++, and it can be any operation. So here I'm just iterating over the n cross m2d kernels iteration space. It can be any operation over here in this accessor. So this is how a generic kind of kernel lambda kernels looks like. There is also another way of writing kernels through function pointers. We'll be coming to that a little bit later, but this is how it looks. So if we go out of this and look at the examples. So let's look at an example over here. So this is the particular example which I was talking about. So the way we write the SYCL kernel is that we use the SYCL header files and the DPCT header files. We use the namespace SYCL. We specify any kind of global context const expressions or any kind of variables that we want to put into place. This is the way to write the queue. So hence we are using the namespace SYCL. There is no need to write something like SYCL. There is no need to write something like this. So because we are using the namespace, so queue, my queue, and then we write the buffers as well. So we are creating buffers, and the accessors is going to access these buffers. So these buffers are like 2D. It can be 2D buffers. It can be 3D buffers as well. So depending upon the memory, the maximum memory block in a SYCL programming model is 3D. So here we have the 2D buffers of data type floats. And here we have the mq.submit, the handler.cgh, where this is the handler that I was mentioning. This handler is kind of like one of the main components of the orchestrator of the command queue. And here we are creating a SYCL accessor or you can create a local accessor as well, depending upon the memory. So the memory model and the programming model will be coming to that a little bit later. As of now, we have a normal accessor, which is a global accessor A, which has only write-only features. Then we schedule a parallel for queue where we have this particular operation in the form of an array of A. And in the next case, we have another asynchronous queue, which is initialize B. So here you see we have three different kind of buffers. One is A, B, and C. So this first one is only enqueuing a parallel queue. The second one is enqueuing a parallel B queue, right? Doing another operation, but the pattern is the same. Here we are creating an accessor B, which is also write only. And here we are also iterating over the 2D range space to fill it some values, right? Now, here is something which is important. I have created something called as a wait, a synchronization barrier, wait and throw. Now this, I'll be coming to that a little bit later, just for an example that here, this is a synchronization aspect. If it is a read-write queue, it is mandatory to have a wait and throw. The reason being that to avoid race conditions and to promote synchronization correctly, because these are all asynchronous threads which are running. So these are all asynchronous work groups rather which are running. So in this case, it is mandatory or sometimes important to have a wait and throw item over here. The next important thing is having another kernel or another accessor, which here we have A, B, which are only read, and C is the write. So what we are doing initially is we are writing to A, we are filling in the values, writing into B as well, B accessors. But in C, we are going to only again write, but here A and B are with read scope. So now we are going to assign the values of A plus B. That means index-wise addition of A plus B accessors to the C accessor, right? And we are going to again backport this C accessor, which is a device accessor, back to the host. So here we have something called as a host accessor. So the host accessor is something which is an accessor on the host. So by default, it is a device accessor. So C is now we are converting from the device to the host, which is only read only. And now we can print the get the results when we by printing the C. Okay. Now, if you want to run this, is SYCL queue ordering. Yeah. So just like I said, you have something called as ICPX minus FSYCL. So FSYCL flag, and we are going to process it for FSYCL device targets. So you can also specify something like FSYCL targets. And you can get SPR64 generation and other generations as well if you have NVIDIA plugins and CUDA and AMD plugins. So here just we are going to keep it simple. And the file name is SYCL queue ordering, SYCL queue ordering.cpp minus o SYCL queue ordering.cpp.o. So here it is just going to compile, and it is going to use the ICPX compiler in this case, and it is just going to, and you can see the output as it is, ordering.o, and it is just going to give you the good computation as it has not encountered anything. So we are actually, this is actually a test. It compares the result with the analytical value or the processed value. This is just an idea of how a SYCL code particularly works. Now there are again different kind of examples, but this is in general how it works. Now, if let us go back to the presentation, right? We have seen queues. Now let's come over here to understand about the memory model in a little bit depth. So like I said, the entirety of the SYCL memory model is kind of like a 3D memory map, so which is known as an ND group or an ND range. So which is shown over here. So the ND range has something called as a work group, and each of the work group have subgroups. Subgroups are a collection of threads, and each of the subgroups have individual work items or an individual thread. So the index space of an ND range group is divided into work groups, subgroups, and work items. All of them run concurrently, but they are maybe scheduled to run at different points of time, like I mentioned, using accessors. And the work group execution may or may not be prompted depending upon the capabilities of the underlying hardware. So this is the memory model of the SYCL architecture. So we have a global memory, like the host accessor, like we saw, or the global memory, or the enum that we saw in the USM, or which is known as the host. So the global memory is one of the important aspects of all the work groups. It orchestrates all the different work groups inside a particular SYCL code. Global memory is persistent across different kernel invocations, concurrent access to a location USM allocation by two or more executing kernels, where at least one of the kernels is modifying a particular code is a race condition. There is no guarantee until we put a barrier, or a wait and throw, or a synchronization. So there are different kinds of barrier and synchronization methods. One of the methods is one which I showed, where we are asking the queue orchestrator or the command queue orchestrator to have a wait and throw. There are other ways where we can synchronize, which is known as through barriers. There are two different kinds of barriers. One is a global barrier, and one is a local barrier. One is the global barrier is for the memory, and the global memory, and the local one is for the local memory and the private memory as well. So this is known as fencing or memfence. We'll be seeing an example on it. So the local memory is accessible to all work items in a single work group. Attempting to access the local memory in one work group from other work group results in undefined behavior. The memory can be used to allocate different variables and shared by all work items. Private memory is a region of private memory to a particular work item. Attempt to access the private memory in one of the work items may result in some undefined behavior. And then there is other important aspect, which is known as the generic memory or the generic address space. This address space is a virtual address space which overlaps all of the three different kind of address spaces that we saw just now. And there is one macro that we are going to use called as SYCL external. We'll be seeing that, where we can ask a particular kernel to stay in a transient generic memory, where it can be accessed through global and local as well as private memory. The important caveat here is that there should be a kind of synchronization or buffers when we are accessing to and fro data from the generic memory. The next important thing is about subgroups. The work groups and the subgroups are the different things of an ND range. So the exposing a subgroup or work items can be mapped to hardware, SIMD hardware. This is a pictorial representation of what happens in the case of work and subgroups. Here you can see that it is a 4x4 work items. That is a length, breadth, and height wise. If I say it in that manner, it is a 3-dimensional 4x cube, where each of the cubes contains 4 work items, and of each of having a dimension of 2 subgroups. So if we specify these 4 items as one subgroup, if 4 items as one work group, then each of these, if we divide it into further, it is one subgroup, and each of these subgroups is going to have one individual thread or a work item that we know. In general, this is the way that we use when we are using SIMD subgroup size. So if we say threads into subgroup size, it is the work group size. In the case of SYCL, the semantics is known as work items instead of threads. So yeah. So the memory scope. Now let's see about the memory scope that we just learned just now. We have the work group, which is the ND work group or the ND range. We have the subgroup. We have the work item, which is known as the thread. And we have something other called as device and system. So these are the memory scope of a particular SYCL header, SYCL header memory scope. Now, let's look into the other important part, which is known as task and data hierarchical parallelism in case of SYCL kernels. So in SYCL kernels, this is the generic kernel code that, or the command queue scheduler, which we have already seen. We are now entering into the parallelism or the heterogeneous parallelism part, where we have something called as a parallel for. Now, there are many kinds of parallel fors. So we have parallel for task scheduling or normal data scheduling, data parallelism, and we have parallel fors for individual work item scheduling inside a particular subgroup or an individual work group. So this is known as hierarchical parallelism. So here we are parallelizing a work group of range 1. It is a 1-dimensional ND range, where we are, and inside this my group, we are getting the main group ID. Think of this as a 1-dimensional array or a simple array, right? And we are getting the 0th index of that particular array, and which contains another work item. So this work item is now useful. We can do some computations on this local work item. So this is known as hierarchical parallelism. This is known as the task or the normal data parallelism or group parallelism. And the last one, we have something called as q.wait, which we have seen in a particular code sample. So this is known as a synchronization. The reason for the synchronization is because we want to ensure that when writing to a particular individual unit of a work item or a thread, it does not interfere with the global subgroup, because a subgroup has a broader scope than a work item or a thread, and the work group has a broader kind of idea over the subgroups as well. So this is what the task and hierarchical data parallelism in SYCL implies. Let's look at an example in this. So if I go back to my code, so let's look at an example. This is a SYCL parallel example where I took the code snippet from. We initialize the queue, which is an in-order queue, right? This is one way of initializing an in-order queue. There is also another way of initializing an in-order queue, which will be coming into the custom kernels. So we get the device, we get the context, what device we are going to run it on, what context we are going to run it on, right? And then we have there are different kind of queues. Like I said, the most generic queue that you will see in most of the SYCL applications is known as a parallel for. This is a parallel for queue, which is encompassing an entire empty range. Okay, so there is no segregation of work groups here. It is instructed that whatever subgroups are there inside that particular work group, each executes asynchronously. Same over here. This is another instantiation where we are including a class template parameter, which is known as a class foo, right? Now there is another kind of invocation which is known as a single task. Single task means only one task will execute, and since there is no other task interfering with it, there is no scope of deadlock or interference, so it will run as it is. Then there is parallel for with ND ranges. We have seen an example like this. Then the most important example that I want to talk about is this one, which I had showed in the just before. So here we have a work group, and inside the work group we have individual work items. So this is a kind of a hierarchical parallelism where we are going down from the work group level to the subgroup level and down further inside the work item to thread level. Okay, the same idea happens over here as well. Now, this is just a simple code for getting, just reading and writing different stuff. So there are also tests. You can take a look at the code. This is just a code for understanding it. And in case if you want to run it, you can just say like this. This is, I think, SYCL parallelism CVP. So you can just compile. It is already compiled in the code. So you can just write SYCL parallelism .cvp minus o SYCL parallelism dot o, and you can get the output. IDs. So in the previous code samples, we have already seen something called as, if it is there, yeah, something like item.global ID or get global ID or something like this, group.get ID. What is this ID? So in accessing memory, or in accessing, I would say, memory locations inside a 3D in a 3D memory space or ND group of a SYCL kernel, right? We have certain kind of functions or templates. Get group ID, ID of the work group, get local ID, ID of the work item inside a particular work group, provided there is no subgroup segregation. Get local range, the dimension of a work item. Get group range. Group range indicates the maximum number of the number of subgroups which can work concurrently. Get maximum local range is the maximum number of work items permitted in a work group. Get group linear ID is the same as getting the group get group ID with the index 0. The rest of the are self-explanatory, where we get the item at the 0. So here we can. So this is how we can access through all these different methods. We can access each individual kernel parameters, or I would say the memory. And the last one, leader, is the leader of the group of a particular subgroup. So let's say generally it is the root 0, or the primary or the first one in a subgroup, in an orchestrated subgroup combined in a work group. So that is how we can access the data. Now, like I said, kernels as function objects. So all of the examples that we have seen, the two of the examples are all including the kernel as lambdas. Now we are going to write kernels as function objects. So kernel can be defined as a named function object because it is there in the same C++ standards. The rule is that it should be device copyable. So there are certain type traits that need to be mandatorily adhere to when writing a particular function, designing a kernel as a function object. So that the first important thing is a device copyable, it has to be device copyable. The operator overloading, it is essentially a kind of a functor in the way how SYCL writes. So the operator overloading of the operator braces, right? Member function must be const qualified, and it may take different parameters depending upon the data accesses. If the operator function writes to any of the member variables, the behavior is undefined. Okay, so here this is an example of a random filler class, right? Let's see this example in more, in a finer grained manner over here. Kernel functions, right? So this is the random filler class, and here you see we are having the same q.submit, we are having the same accessor, but we are not having a lambda that we used to have. We are not scheduling a parallel for, right, in a lambda format. We are scheduling it for in the case of a function argument, right? So as function objects. So here we have something called as a random filler, which fills based on a random distribution of data. Here we are getting a buffer. We are setting a queue and a constant range R, range for the distribution. And we are inside the parallel for, we are calling this instance of this random filler class over here. So which overloads this operator over here. Okay, this overloads this operator, and you get the get ID, and you call this get random function, which returns this random num over here. So which is initiated with the rand distribution. So here we can see that instead of using lambdas, we are using function objects. This is another way of writing the SYCL kernels. Now, which one is more performant than other? It is typically not a question, because it depends upon user to user how they want to write the code. In most general practices, lambdas or stateless lambdas are used, but in some cases you can also write function pointers, function objects. Kernel cell lambdas we have already seen. Like I said, there is the most important trait for having not only for kernel for function objects, but also kernels which are, I would say, lambdas. So the most important thing is having device copyable attribute. So device copyable must ensure CPP 17 unary trait requirements, and device copyable means that whatever type trait your parameter, your variable has, it must adhere to the centralized template type trait, which has with which the kernel has been initialized, or I would say with which the kernel has been initialized. So if device copyable is specialized such that is device copyable v of t having the template type name as t is true on t, that does not satisfy all the requirements of a device copyable type, the results are unspecified. So it is mandatory to have the template type name, right, the centralized template type name t, whatever it is, to have the same to have the same type trait for this particular variable. So it should be inheritable. In other words, it should be having the same type trait. This is one of the most important features, or I would say the clauses of writing any SYCL kernels or through template parameters. These are the type of the following SYCL types of legal parameter types. So when you write a accessor, when you write a USM, these are all falls within that particular type trait. So device copyable type trait. So there is no need to worry about that. So including images in the case of buffer images, in case of SYCLs, in case of streams, in case of accessing memory through ranges, IDs, arrays, vectors inside SYCL or scalars inside SYCL, all of them are within the standard bounds or within the standard bounds of device copyable trait. So there is another trait which is known as group functions. Group functions are extremely important when we want to schedule different kind of synchronization barriers, as well as operations like reduction, as well as operations like shuffling and other operations. So group operations operate on work groups, and they are most performant on accessors as memory parameters. So this is the typical group structure in SYCL. So is group const expression bool is group should have the type trait. Again, it should have the device copyable type trait. So the group functions inherits from the device copyable type trait. So for example, this is like I mentioned in the case of global memory, there needs to be a kind of a fencing to avoid race conditions. This is a group barrier. So a group barrier has memory scope fence scope, group fence scope. So this is one of the group barriers where we can use that. We will be again seeing an example where we have a local fence fence scope. So group functions are extremely important, and it should have the type trait. Then the third most important part is address space. So we already talked about global address space, local address space, generic address space, private address space. We talked about accessors having different kind of address spaces. We have host accessors, we have the local accessors or the default accessors. For accessing the accessors, right, if you want to access a particular index of a particular accessor, we use something called as a multi-PTR, which is there in the C++ standards. So this is a syntax general for accessing a DSCC, which is a local accessor, right? We get the multi-PTR attribute. This is a non-template accessor. So that means it is either, it has a definite type. So it is int, float, or SYCL half, or any kind of that. So it is not having a template type name. So dscc.a is a kind of like, let's think of it like a local accessor, which has a get multi-PTR, and we are going to use the get method, and we are getting the multi-PTR pointer in this case for that. So there is also an explicit pointer class called as a global PTR, which is known as get global PTR if we have a host accessor which is accessing on the global scale. We also have a generic address space that I talked about, which works in the transient generic memory space, which is through the SYCL external attribute. So if you want the kernel to be in the transient state where it can be accessed by host device, that means the global, local, and the private memory, you can have the SYCL external attribute as well. Now, this is another kernel example. We are copying 2 to the power 10 cross 2 to the power 10 across 16 work items through SIMD. So here we have this is a USM kind of a syntax. Here we see malloc shared. These are all USMs. This is not an accessor model. So just an example for how vectorization. This is actually an example of vectorization in SYCL, where we are getting two data. We are mem setting it, and then we are getting the subgroup, individual subgroup, and the range of that subgroup, and then we are performing some computations to copy blocks of 2 to the blocks of 16 work items. That means in blocks of 16 threads, 2 to the power 10 cross 2 to the power 10 items. So that is one array contains 1024 and the other array contains 1024. The next important thing is exception handling in SYCL. So queue wait and throw is one of them. Queue throw asynchronous is another. Event, there is another thing called as an event. So similar to queues, we have something called as an event in SYCL, where we can also have an event, which is another orchestrator to wait and throw. This is a typical exception handling mechanism in SYCL. How we would write, we would get the context, we make some error or write some code over here, we catch it through the SYCL exception, and we also raise an error code in SYCL. So this is how we write a SYCL exception. So when you initialize a code with a queue, when we initialize, it is important that when you write this particular block of code, inside your queue, you should have this wait and throw or wait asynchronous. So the next important thing is synchronization, like I talked about. So synchronization is one of the things that we have already seen. The other important thing is synchronization through using the device event attribute. So this is the device event class in SYCL. A device event means that if your code is running on a SYCL device, and if suddenly something comes up, like some race conditions comes up, you would want to have an asynchronous device event which can synchronize this particular which can synchronize the kernel threads. So this event can be used the wait and throw. So this can have the wait and throw attribute over there as well. So device event, and inside that namespace, you can have wait and throw to synchronize that. So this is how the device event class looks like. So this function wait is the by default function which you can use to synchronize. There is another synchronization method for atomic primitives inside SYCL, which is known as atomic ref. Atomic ref asynchronous provides the ability to perform atomic operations in device code, but this requires some memory ordering. Now, this is contrary, this is opposite to C++ standards. So atomic refs in C++ standards, they generally have a memory ordering. In the case of SYCL, it is not so. We need to specify a memory ordering. Now, the memory ordering in SYCL is a little bit different. we have to specify what memory ordering there needs to be, whether it is in the global memory ordering or it is in the local memory ordering. We have to specify, as we know that reduction is kind of like a shortening of a particular container to a specified, or by a specified operation to a shorter value. It can mean multiplication, addition, subtraction, and other arithmetic operations as well. So this is a different way of writing the SYCL kernels. Now this is, as we know, USM kind of format. We have already seen accessor kind of format. Now let's look into the USM format. Here we have an integer array pointer which is known as the buffer data. We are using malloc device. This is not malloc shared. I can write malloc shared, but here I'm using malloc device to show you an example how to copy from the host to the device as well as after the operation back to the host. So here we are initializing a buffer data of malloc device, and we are specifying a q mem copy of buff data, right? Here we are copying the data from the host to the device. We have the standard scheduler. We have the parallel for, and here we see a typical example of a 3D kernel or a 3D range. Here it is a ND range of size 3, right, of dimensions 3 of 128 blocks. So here we are calling a block reduced kernel. And after the block reduce kernel gets called, we are back copying the data to the from the device to the host, right? And this is the block reduce kernel. So here we are accessing the thread.get local ID. Now we know what get local ID is. Now before we know this what get local ID is, but what is this parameter 2? To know the parameter 2, let's look at some one slide where I have mentioned this. So because SYCL was originally developed to be almost compatible or comparable with the CUDA language, there are certain translations from CUDA to SYCL. So in CUDA, the three-dimensional arrangement that we normally know, right, in which is known as host and device, right? We have a three-dimensional block kind of agreement in CUDA as well. It is known as blocks and grids. Here we have work groups and subgroups. Here we have blocks and grids in CUDA. So here, the grid dimension XYZ is represented as item.get group range 210. So here you can see that 2 represents X, 1 represents Y, and Z is represented by 0. That means the order is inversed in the case of SYCL. So here, get local ID2 that is used in this particular code that we are seeing, get local ID2 indicates that I'm accessing thread idx.x. I'm accessing the X of the X parameter of the thread, three-dimensional thread. So just as an FYI, how this mapping happens from CUDA to SYCL. Block dimensional is known as get local range. Block IDX is known as get group. Thread ID is known as get local ID. Warp size is known as get subgroup, get local range dot get 0. Okay, so yeah, so here we are getting the X thread idx.x if it were in CUDA. Then we have the thread ID, we're getting the thread ID, and we are performing a reduction operation which SYCL has, SYCL reduce over group, because we are reducing over the group. We get the get group, we pass in the input data, and the operator is plus operator or the addition operator. It can be SYCL maximum, it can be SYCL minimum, it can be different kind of operators. Here we are using the addition reduction. And we are assigning the thread data to the data array, or I would say the device array. Right. So this is a particular example where we are using this. So you can compile it and run it. The source files and the compile files are already there. So let's look at another example, which is known as which is almost if you have done some CUDA coding or have experience in kube APIs or kubeless APIs, there is something called as memory accessing and sharing of memory to and fro, storing different kind of storing a particular container in different memory formats and accessing them in different formats and so on. So this is a particular example which stores and loads the data in blocked format and striped format, which is kind of different formats in CUDA. So here we have a similar kind of a buffer, this accessor model. So here we have the local accessors. Here we see two different kind of accessors. One is the local accessor, one is the accessor. By default, it is the local device accessor. So local accessor means that it will go to the local memory space, or generally it is the private memory space if generic is not mentioned. So here we are scheduling the 3D range kernel. We have a thread data which we are going to load so what we are the main attempt of this particular block of code is we have 128 cross 128 cross 128 grid block, and we are going to load these 3D dimensional grid blocks in 4 items in using 4 threads, or I would say 4 work items, and each of these work items will take up 128 divided by 4 subgroups, right? And they will be putting it back in the different manner in the memory. So hey, like I said before, we have already seen this, how to access, get multi-PTR attribute, how we can access that using access local accessors. Here we see an example. We are accessing each of the pointer, the multi-pointer, because it is a kind of an iterator which not only points to one of the element, but because since this is a 3-dimensional pointer, it points to a 3-dimensional grid or 3-dimensional work item or a 3-dimensional thread. Okay, so that is why it is important to have get multi-PTR and use an accessor model over here. We have this accessor model which passes in the load stripe. The size is 128. We pass in this multi-PTR attribute and pass in the thread data, which will pick up in blocks of four work items or 4 threads. And this is how the load operation happens. We see the reduction is already there. So after the load, some reduction operation we are doing, and after that we are storing it back into the host memory. So the loading is something like this one. So for every items, we are loading the block iterator. That is, a block iterator is your multi-PTR. So it loads loads your item in blocks, in contiguous block elements, and provided with some offset. Okay, and this loads in blocks of 4 work items or 4 threads. Okay. Similarly, while deloading or unloading it back to the host memory, we are having each of these 4 thread items or the work items, right? Each of these 4 work items, they are concurrently and asynchronously, they are unloading it back to the items namespace or the central 3D memory block. Okay, so this is a typical example where you can use load and store or a kube API translation of your load and store to your SYCL standards. Let's look at another example or a variation of CUDA, which is an integer quantization kernel, right? So this is a simple quantization kernel where we perform bitwise quantization to the same thing. So here we have an USM model, right? We just calling the data as it is. Rest of the things are just the same. If we look into the codes, you will find that majority of the driver code and the command queue initialization is either USM based, memory pointer based, or accessor based. So it is almost the same. We are calling this function, which is a device function, and we are getting the global ID 0, which is the Z item. This is actually the Z item because 0 is Z for CUDA, right? So auto scale value, and we are getting we are compressing the bits, just like we normally would. This is standard C++ operation code to compress it and get the quantized results in either 8-bit or 2 bits. So all of these kernels that you see are deep learning kernels, are used in deep learning kernels. For example, this is a softmax kernel. Softmax is one of the activations which is used in deep learning. It is an exponential kernel where it is used as an activation function in majority of the deep learning applications and frameworks. Here we see a similar kind of a accessor model. Here we are loading into memory using blocked approach, contiguous approach. Striped means interleaved approach. Blocked means contiguous approach. Striped means interleaved approach. So we are loading in the block format, and then we are doing block softmax kernel. That means we are not doing softmax on an individual work item. We are doing softmax on subgroups or either or combination of subgroups, right? So we are doing a blocks, let's say 128 0 to 127, and then 128 to 255. So like this, we are doing softmax on a block kernel, so 3-dimensional block kernel. So the operation is just the C++ operation. We are using a max of SYCL fmax operation, which is similar to the maximum operation in C++, and we are just doing a numerical operation. So for reference, softmax is something like this one. So this is what softmax looks like. So here is an exponential Zi where we are summing divided by the sum of exponential Zi. So it generally normalizes your values from 0 to -1 to +1. And this is what we are doing over here. So we are getting the max of the data, and we are getting this. We are getting the SYCL exponential exp from data minus the Maxwell divided by the exponential sum. Okay, so this is how we do the block loading. You can look into the code to get a little bit depth. You can run this code as well to get the outputs as well. So now let's move back. We have seen a couple of examples of custom kernels. Now let's look back into the some other aspects of CUDA SYCL. So the code that we write in CUDA, the code that we write in SYCL can also be used to mimic CUDA and made to run on CUDA specific hardware. So to do that, we write device.getPlatform.getBackend one API CUDA. So ext1 API external SYCL backend ext1 API CUDA will indicate that you want to run it for the CUDA backend. The generated PTX ISA is usually comparable with the native NVCC compiler when using the same optimization flags. And same thing is happening for the ext1 API AMD as well. So for the AMD platforms, CUDA driver and HIP driver are also there. And if you want to compile for the CUDA and the HIP, you can specify if SYCL targets either AMD GCN, AMD HSA, or NVPTX for the NVIDIA compiler or NVCC compiler. And the rest, SPR64 is already we have seen. We are just running it now. So this is the code sample that we just take a look. Reduce over group, block reduce, how it looks in the CUDA sample, how it looks in the SYCL sample. So we have already studied this. This is the way the code looks in the CUDA APIs when we write the CUDA code. If we use the DPCT tool, it will also get migrated. This is another example where we have convolution kernels, CUDNN convolution forward, CUDNN, and you have CUDNN's device synchronize. Similarly, we have the APIs for async convolution forward. We have the queue wait and throw that we have seen. We have the convolution descriptor as well, like in CUDA. So when you use the DPCT toolkit with the DNNL flag, one DNN flag, it will automatically translate your code from convolutions. We have already seen the softmax example with pure SYCL. This is the softmax example with CUDNN. We have the softmax forward in CUDNN. We have the descriptor of softmax forward, mem copies and everything. We have the similar kind of mem copies for the SYCL side. We have the async softmax forward for the SYCL side, and the queues and scheduling, everything is there as well. And now let's look into a little bit about the custom how the SYCL comes into the picture in deep learning case. So for a framework, let's see in a case study with a framework, let's say PyTorch, for example. So PyTorch is the most popular framework in the case of deep learning. It has mainly graph kind of deep learning architecture where it kinds of lowers down. It creates where we write the code in Python, which creates the graph for us, and then we have the graph lowering where it boils down to the different lower level primitives, compute primitives, A10 primitives. A10 is one of the compute backends of PyTorch intermediate representations, and then there is some graph lowering where it boils down to specific ISAs or device specific bytecodes. And PyTorch is one of the accelerator runtimes. To make SYCL compatible with PyTorch, the only way to do it is, there are many ways to do it. The most popular way to do it is through CMake. So the code that you write in SYCL, right, we have to have a kind of a torch extension. PyTorch provides extensions for combining different kind of CUDA code as well as SYCL code. If you want to, the only caveat here is that if you want to combine, let's say you have code written for the SYCL language for the Intel primitives, that means you have compiled it for the ICP-XF SYCL flag for SPR64 generation, right? That means your SYCL code is compatible with Intel. So Intel hardware. So your torch extension should be specified for DPCPP extension instead of CUDA extension. So similarly, if you have a SYCL code which is targeted for NVPTX target, right? That means the CUDA target or NVCC compiler, right? In that case, you can use the torch extension, dot standard CUDA extension, to automatically in your CMake to link your binaries together and to get your source files. So once you have the source file CMake, you can link and run your Python front-end code to call this SYCL invocations, and you can write them. So this is a case study of transformers where we have 4 individual, which is a kind of a architecture which is running most popularly in all deep learning applications. Majority of the deep learning applications like ChatGPT and LLMs and llamas and everything. So here we have one of the important, interesting features where we have 4 attributes in this: positional encoding, self-attention, normalization, and feed forward. Each of these blocks are repeated number of times to get the transformer architecture. And in example, we have a kind of a, I would say, The SYCL with PyTorch folder inside GitHub has the transformer kernels, which are written in pure SYCL kernels. So you will see the SYCL activation kernels. We have the SYCL layer norm kernels. We have the attention kernels as well. You can link them through the CMake. So I will just go, for brevity, I will just go into the activation kernel, which is a GALU activation. Here we are seeing something called as, we see the normal, I would say the SYCL kernels that we have already, the queues and orchestrators, everything that we normally write. These parameters are SYCL buffers, as SYCL ranges, as well as something called as scalar T, which are PyTorch ops. So PyTorch C++ operators, which can be used with either CUDA or SYCL. So if the scalar T is one parameter, which you will find majority in the code, which is a PyTorch op, which is C++ usable, right? So here we perform a different kind, where we call a kernel which is known as CILU mul kernel, right? Which is an activation kernel, and it gets called over here with CILU activation kernel, and this is performing some computation. So you can take a look at this particular individual kernels, this layer norm kernels and everything, which is written in pure SYCL. There is no PyTorch inflection apart from the data type. So how to link them? We link them using this. If we go to this, the setup.py, right? If you go to the setup.py, the only interesting aspect is that if built for SYCL, then here we are using something called as a torch CPP extension, which is known as DPCPP extension. Because we have SYCL code, we need to compile for inter targets. So we need to have the DPCPP extension. We pass in the compiler CXX flags, what we want, what kind of optimization, let's say O3 optimization we want to have, 20 standards or 17 standards, whatever it is. And then we pass in the source kernels to get compiled, right? And we use this DPCPP extensions to compile those. Now, had it been the CUDA kernels, we are going to write the CUDA underscore extension from torch.extension.CUDA extension for if you want to have CUDA compiled binaries from SYCL. Okay, so this is how we write the code for the transformers. The entire transformer code is present over here in the case of SYCL kernel. So DPC++ compiler is the Intel's proprietary compiler, which is used for auto migration of CUDA code to SYCL code as well as compiling. Okay, so this is the outline map of how the DPC++ code gets compiled. So you have the user make file, intercept build, right? The CUDA source files. You have the CLang headers, which are already inside DPCT, right? And it gets converted into the DPCT code. We'll be seeing an example use case of this. So DPCT -p in root and keep original CUDA code. So this is one of the ways we can specify DPCT and then pass in the arguments, whereas the in root contains the in root of the of all the CUDA code, including the CUDA headers as well, and the output where you want the DPCT output. It is also interesting and important to mention the CUDA headers as well, because there are some aspects where you need customizable CUDA code to be transferred to customizable SYCL code or DPCT code. Building and to migrate a project first requires building the DPCT target. So first you have to clone the cyclomatic repo. You have to build the cyclomatic repo using Ninja, CMake -g Ninja. You have to specify the C2S install folder. We have to specify certain extensions. So what targets do you want to build for? x86 target, MVPTX target, right? We want to have the CLang extension for it, and then install for the Ninja C2S. Okay, and after you have installed it, this is the generic by default or the de facto method how you are going to convert a SYCL code to your CUDA code to your SYCL code. So in root path to your CUDA project and the output path to your SYCL code. Okay, so generally the output becomes something like CUH files gets converted to dp.hpp and cu to dp.cpp. There is also a feature called as incremental migration. You can also specify no incremental migration, so that whatever has been migrated, so if you are working on a big project and let's say some of the CU files are already migrated to SYCL or the CPP files, dpcpp files, you do not want to remigrate them again. So you can specify no incremental migration. It has also you can also have experimental features like user-defined migration and user-defined rules as well. We'll be seeing an example. Let's see an example on this. This will be the last example of today. And for this, let us go into the DPCT folder inside the rep. So here we have a live example. In this live example, we have two separate files which are already open in my case. So we have something called as simple kernel, simple CUDA kernel. Okay, so this is a simple CUDA kernel, right, where we are specifying This is just a simple kernel or a hello kernel of grids and of CUDA taken from the CUDA standard examples. We are mallocing it, we are memsetting it, and we're just calling a kernel just for getting what is the output of the blocks and the dimensions. Okay, and we are arranging it from a certain value. Just a mathematical operation inside a grid and a CUDA grid. Okay, so the translated code is also present as comments over here, just in case. So we are going to transfer it. We are going to translate it using the DPCT toolkit. So so if you specify DPCT help, you are going to get a lot of options. Here you have to pass in your CUDA headers. The reason for passing into your CUDA headers is because it may contain some grid and some fancy kernels and also which might be important for your use case. So you specify your in root, which is your DPCT / live example, and you are going to have an out root, which is DPCT / DPCT output. Okay. And that's it. I think you can also specify certain other arguments like, for example, USM level none. Or if you want to have no formats, you can write format use format equal to none, right? So also, yeah. So there is also another important thing. If your code does not contain a main or a driver code, you can pass this flag process all. So this will by default translate and parse all of your CUDA files to your SYCL files. This is essentially important because let's say you have host device or you have kernels which are host and which are device specific, which does not have a main or a driver code. In that case, you can use the processor to migrate the code file as well. So if you go to DPCT output, you will get the CUDA kernels .dpct and yeah, you see that the kernels are translated to this particular aspect. You see the same code over here is getting over here. So you are going to see the dimensions and everything, the SYCL kernels. So the grid gets transferred. So the grid one. So for example, over here, let me just, yeah. So the grids over here, all the grid logics and the kernel invocations over here, it is getting transferred to command queues and parallel force in the last example. See, so this is how you migrate the code. Now, once you have the SYCL code, you can compile it for InvitPTS targets as well in the ways that I mentioned or any other targets. So you can have the SYCL code running on CUDA hardware as well. Other examples are also there. For example, if you want to just migrate, for example, let's migrate another function. So already I have the migrations present over here. So I have the DPCT output over here for one of the functions, which is CUDA USM .dpcpp. It is taking from the CUDA USM from the CUDA code. So this is over here. So let me go back. So yeah. So there are other examples, cooperative groups, and other fancy examples. You can also migrate it at your will. So so this is the CUDA USM.cu file, right? Here you see the unified shared memory access and the malloc access in the case of CUDA, right? Which is another simple, simple kernels, right? Accessing and deaccessing. Okay. This gets translated to this CUDA DPCPP. So if you see, you are going to see a lot of parallel force, queues and everything over here as well. So the kernels get into parallel force. I mean the command queues. You have the mem copies from CUDA mem copy malloc device. So the CUDA memset and the CUDA malloc gets converted to the malloc device and malloc shared, whatever it is. And yeah, I mean you can definitely translate and run your CUDA code to SYCL code. So there is also another aspect which is known as user-defined migration. So for example, just one example, this is the last example for today. So you have the user example, user-defined. So let's say I'm doing device scan, which is one of the CUDA algorithms where we are scanning for CUDA user-defined scan. So this is a CUDA header or a CUH file. So here we are calling curb device scan API. and this is a CUDA source file, the corresponding CUDA source file. Once again, which sorry. So CUDA user defined scan. So it is calling this user defined scan function, right? Now also here we are performing passing a rule, which is a rule which takes over the CUB device scan and the CUB device scan inclusive sum in and out, and also includes these two headers, so that these two headers can take over these two invocations and convert them to the SYCL, or I would say I would say the semantics similar to the SYCL side. Okay, the CUB API similar to the SYCL side. So the way to run this is to have this invocation over here. We pass something called as rule file minus rule file, where we pass a YAML file which contains the rule invocations. So this is how you can also migrate user defined specific code translations as well. Okay, so this is the last example for today, and that is the majority of the. You can also, there is also one example on the kublas APIs, so which are matrix multiplication. If you know kublas, it is used for extensive matrix multiplication. You can also use this particular command, dpct usm level none outroot, and specify the in root. CUDA include path that I mentioned, using the same code, same command that I mentioned. CUDA host only specifies that this kublas code migrated to SYCL code will run on the host only, and you can get the SYCL code of that as well. So that's it for in terms of the majority of the SYCL language, DPCT compiler. And to end, I would just say so we have covered all of the intrinsics and the majorities of how to write SYCL code, how to design kernels, memory models, synchronization, host device, programming model. We have also seen DPCT toolkit, translation, migration, as well as writing custom kernels in SYCL. And we also have some performance numbers, just in case, how it works in CUDA SYCL. We have the SYCL numbers for AMD as well. These are some of the, this is for the AMD SYCL versus AMD HIP on AMD GPU. This is for Llama 3 benchmark, which is a deep learning model on ARC 770. Performance in terms of latency, right? How fast we are generating the latency, which is run on the Intel stack chain over the SYCL code. It shows how performant we are in deep learning applications as well. The AMD SYCL is the blue one over here. Similarly, the CUDA is over here. NVIDIA SYCL is the blue one. So some resources and codes are present over here for reference, just in case. And I'm open to questions and further discussion.